All right. Hi, guys. Very good evening, everyone. Welcome all of you to Home Institute. Welcome to this session. And here we begin up IIT Madras PYQ series. The questions asked in yes, so the IIT Madras PYQ series. Okay, the question asked in the years, okay, where the GATE examination was organized by IIT Madras and they were respectively 2019, 2011 and 2003. Okay, in one of the previous video which was uploaded very recently on our YouTube channel, okay, we have presented the complete analysis of the papers conducted by IIT Madras in terms of difficulty level, in terms of the weightage, not only subject wise weightage but also chapter wise weightage. Okay, from which subject which chapters were being asked more. Okay, that was a trend analysis done for all subjects and all chapters of all subjects. Okay, and now we are going to discuss actually those questions. Okay, of like control systems. Today control system is common to EC, so we are going to discuss the questions for both EC and EE. Okay, and because the number of questions are good enough, we have split it into two parts. Today we'll discuss fundamental 1 mark questions. Okay, the fundamental 1 mark questions. Okay, so all those students who are also parallelly preparing for the upcoming AEE examination of AP Genco Transco Discoms. Okay, and because the number of questions for them also, this session specifically 1 marker, okay, can help them. Okay, so let's get started with this session. Okay, and the next session I'm telling you today itself will be control system 2 mark session. Okay, the next session will be control system 2 mark session. Today let us see 1 mark, all 1 mark questions. Okay, right, and then subject to subject, we'll keep announcing it to you. Okay, so here it is. If you look into this one, and before I begin up, okay, important updates is, okay, for GATE 2027, the new offline batch at our Hyderabad center, okay, for electrical starts July 29. This is the update for electrical student, that is July 29, the next offline batch, okay, at our Hyderabad center. Okay, then similarly for EC, the new offline batch starts August 4. Okay, for August 4. So you can enroll today, you can start your preparation, and still you have enough time to fight and compete for the GATE examination. Okay, because of course many might have started earlier, but last year I gave examples also. Last year several students started from July, after mid-July only, and they got ranks under 100. If you talk about me personally, I started my preparation somewhere after 20th July only. Exact date I don't remember, it is so many years, but I remember, okay, when I was in 5th semester, after 20th July somewhere I started, and in my first attempt I got 9th rank. Okay, so time, it totally depends on you. You can make this time also a sufficient time, okay, provided you put up your consistent hard work. Okay, yeah, definitely. So that also is there in our mind. So we'll be starting a series, based out of a new pattern of questions, unique questions. Okay, workbook based series also we'll be starting up here. Okay, so yeah, let's get started here now. Okay, with the first question for the day. Okay, the inverse Laplace. Now this question typically can be a controls or a signals question. Either ways you can place it. Okay, the inverse Laplace transform for this given signal. Okay, Hs equal to s plus 3 upon s square plus 2s plus 1. But this one is pretty easy and it has to be 1 mark level question only. Okay, so this is GATE 2019 electrical 1 mark question. Okay, easy only. Okay, why? Because if you just see the pattern of the denominator, okay, if you see the pattern of denominator is nothing but s square plus 1 square plus 2 into 1 into s, a plus b whole square. So denominator is nothing but s plus 1 whole square. S plus 1 whole square. Then what can I do? Okay, because it is s plus 1 whole square, you can split the numerator as s plus 1 plus 2. Okay. Okay, now the things become easy. Okay, so on this, if I divide out the first s plus 1, okay, I'll get 1 upon s plus 1, 1 factor cancelled, and next 2 upon s plus 1 whole square. Okay, now you know what the answers is. Okay, by this time some answers might have come up. See, okay, see, for t greater than 0, I mean, for t greater than 0 means assuming causality. Okay, so which signal? E power minus t. Okay, e power minus t or e power minus t ut. Okay, the Laplace 1 upon s plus a, or if it is e power minus at in general. If it is e power minus at in general, t greater than equal to 0, I am assuming, so I am not specifying ut. And if it is t e power minus at, then you say 1 upon s plus a whole square. These are the Laplace transform pair here. Correct. Okay. So what is the inverse Laplace ht here? Okay. This corresponds to e power minus t, and 2 is constant here. This one corresponds to t e power minus t. Simple one here. Okay. Option number B you can tick mark. Option number B is what you can tick mark here. Correct. So yes, Sirisha and Tharun, correct answer. B. B is what is the correct answer. Okay. Chalo. Next question then. Let Ys be the unit step response of a causal system having the transfer function Gs equal to 3 minus s upon s plus 1 s plus 3. Okay. That is Ys equal to Gs by s. What is the forced response of this system? Okay. What is the forced response of this particular system? Now understand here. Okay. The forced response of this particular system. Okay. Forced response. In a way, okay. Let me first calculate and then talk about this one. Okay. Correct, Prudvi, also B answer correct for the previous one. Now see here, Ys be the unit step response of a causal system. Okay. So, you know, this is the complete transfer function. The system has the transfer function Gs. Okay. So, Ys is Gs upon S. Why? Because, okay, it is the unit step response. What is the unit step response? It is the output or response for step input, for unit step input. Okay. And how do you anytime write down the output of any system? If this is the transfer function, transfer function is the ratio of output divided by input. Okay, suppose the input is Rs, Ys upon Rs. Let me take it this way, or let me call the input as Xs, anything you can name it here. Y by X. Okay, so Ys is actually what? Input into gain. Okay, and the input in S domain, because it is the input, we have to take a step input. That is what is 1 by S. So for that also they have given it clearly. It is Gs upon S. It is Gs upon S. Prudvi say answer C for this one. Let's check it out. Okay. Now, this is Gate 19 EC 1 mark question. So see here, first of all, okay, again basic Laplace calculations will come up here. So when I substitute Gs upon S, Ys will become how much? Okay, this 1 by S will come up here. So it is going to be 3 minus S upon S, S plus 1, S plus 3. And first of all, I should be converting it this way. A by S, B by S plus 1, C by S plus 3. To calculate the inverse Laplace, I should split into partial fraction. Okay, na? Right. So I have just splitted this into partial fraction. Now I want ABC. Okay, to find ABC, I'll multiply throughout S, S plus 1, S plus 3. Or you can use residue method as well. Okay. So left side 3 minus S. This multiplied whole throughout. Okay. So when you multiply, S will cancel here. In the first term, S plus 1, S plus 3. Plus, the next term, S plus 1 will cancel. You will be left with B, S, S plus 3. And in the third term, S plus 3 factor will cancel. C, S, S plus 1. Okay. Now, if you have to calculate A, you should make the B and C corresponding term 0. Okay. The common factor in B and C is S. Okay. So, I would start here by taking S equal to 0. If I take S 0, this is 3. This is A, this is 1, this is 3. So 3A is 3, 3 you cancel, A value obtained is 1. Okay, now for B, I will look into common factor in AC, that is S plus 1. So I will make S plus 1 0. How will you make S plus 1 0? By taking S equal to minus 1. So 3 minus minus 1 will be 4. Okay, A and C term will be 0, only B will be left, minus 1, and minus 1 plus 3 will be 2. Okay, so this will give me how much B? 4 upon minus 2. Okay, so B will be minus 2. Okay, and then common factor in AB is S plus 3. So put S plus 3 0. That means S equal to minus 3. 3 minus minus 3 left side 6. Okay, C into minus 3 and minus 3 plus 1 is minus 2. Okay, 3 to 6 minus minus plus 6 and 6 cancel. C value will be 1. ABC everything obtained. ABC everything is obtained. Now please see here. Please see the next calculation. So what it is going to be now Ys. Okay, now Ys, okay, if I have to write down the forced response of the system, okay, first I'll write down ABC here. A was 1, 1 by S, B, minus 2, B is minus 2. So minus 2 upon S plus 1 and C is again 1. Okay, and 1 upon what? 1 upon S plus 3. Now convert into time domain. Take the inverse Laplace transform. What is yt going to be? Okay, this is 1 upon s corresponding to 1 or ut minus 2, 1 upon s plus 1 e power minus t ut, and then 1 upon s plus 3 e power minus 3t ut. Okay, this is the response of the system. Now understand here, this is the response of the system. Okay, it is causal system. That is why I have taken every signal as ut signal. Okay, as the ut signal. Acha. Now, this is the response. The question is specifically asking forced response. Okay, forced response. Okay, also in a way represents steady state response. Okay, which of the part? Okay, see, this response has to be broken into two parts. Okay, but what happens when t tends to infinity? Okay, this is going to become 0, e power minus infinity, e power minus infinity. Okay, so when the time becomes large, these two terms go away. This will be representing the transient part. Okay, this will be representing the steady state part. This will be representing the steady state part. The transient part and the steady state part. Okay, the transient part, okay, natural response. We break the system also into natural response and forced response. And this part, we'll call it as the forced response. Okay, so when t tends to infinity, this steady state part or forced response will be obtained as limit of t tending to infinity yt. Now, when you put t tending to infinity, e power minus infinity 0, and what is only going to be left is ut. So I did not ask the entire response, I asked the forced response, and that is going to be ut. Okay, that is going to be ut, in a way steady state part. Okay, right. Praveen here says D. Okay. No, D is the total response of the system. That's what D is. What is the total response of the system? Hope you got this now. Okay. Now, if this is what I want, okay, we can do one more thing in this question. If this is what I wanted, what is the one more thing that I can do this question? I can do to this question. If this is what I wanted, think. What is that one more additional thing I can do here? Okay. Simple technique is, okay, if I eventually wanted the forced response, okay, which I told you as steady state response also, which means limit t tending to infinity yt, which can also be solved as limit s tending to 0 s into ys as per, okay, steady state or final value theorem. As per the final value theorem, we can also solve it by this way. Understood? Yes, okay, Prithvi. Okay, so, okay, no need to do all this random calculation. Limit s tending to 0 s into ys, and what is ys? No need of any partial fraction and all. I'll just take this ys, which was given as gs upon s, this expression without any partial fraction. I'll go and substitute there. Divide 3 minus s, divide by s plus 1, s plus 3. Okay, and when I do so, s and s cancel, and then when I put s tending to 0, 3 upon 1 into 3, and that is going to be 1. 1 means ut. Okay, for t greater than 0, automatically it is causal. 1, or you can call it as ut. The output is going to be 1. What is the answer left at, steady state? 1. We will call it as ut. That's what. This is a simple shortcut to calculate. Okay. Rather apply the direct final value theorem here. Okay, right, but yeah, you should know that. Okay, but you should know that writing as a condition for final value theorem, all poles, to apply final value theorem, all poles must lie in LHP or at most one pole allowed at origin. Okay, there was one pole at origin, that is okay, but these are poles at -1 and -3. At most one pole allowed at origin. Correct? This is the concept behind the question. Next question, 2019 electrical 1 mark question. They are directly asking the steady state value of yt. Okay, so the output response of a system is denoted as yt, and its Laplace transform is given. What is the steady state yt? What is the steady state value of yt? Okay, steady state value of yt. See, yt, the Laplace transform ys, it has a pole at origin and this will be two complex conjugate poles in LHP. Why? Because you know that if it is a second order term, okay, if it is a second order term, okay, this coefficient positive means zeta positive. For second order term, the central coefficient s is the coefficient of 2 zeta omega n. So if zeta positive, if this coefficient positive means zeta positive, and zeta positive represents LHP roots. Okay, so no problem in applying the final value theorem. Again, this is a direct question that we can solve it by final value theorem. Okay, so limit steady state value t tending to infinity yt is equal to limit s tending to 0 s into ys. Okay, limit s tending to 0, substitute ys, that's it. Okay, that is 10 by s square plus s plus 100 root 2. S and s cancelled, and now when you put s tending to 0, 10 divided by 100 root 2, 1 by 10 root 2. 1 by 10 root 2. Option D. Option D. Correct answer here. Yes, option number D is the correct answer. Yes, Shirisha, correct. Option number D. Okay, option number D is the correct option. Then let us move ahead to the next question here. Okay. Next one. The differential equation, okay, 100, okay, d to gate 2011 EC 1 mark is given to you. 100 d2y by dt square minus 20 dy by dt plus y equal to xt describes the system with input xt and output yt. The system, which is initially relaxed, is excited by a unit step input. Okay, it is excited by unit step response. The output yt can be represented by which waveform? Okay, now see, when you convert to the S domain, no need to convert, but just remember, if you are converting and finding the transfer function, okay, this will correspond to S square, second derivative, and this will correspond to S. And because this is going to correspond to S, okay, what is the coefficient of S is negative, and this will indicate that zeta is negative. Okay, zeta negative represents unstable system. Output will become unbounded. It will grow with time. Okay, it will grow with time. Okay, that is what you can directly mark. This is how you should treat a 1 mark question. Answer has to be A. Okay, answer has to be A. Because this is what? This is underdamped waveform. This is obtained for zeta between 0 to 1. Okay, this is like overdamped. Okay, this is like overdamped. I think there is some typing error here. Here the intent was to make a critically damped. Okay, which reaches equilibrium as quickly as possible. Which reaches the equilibrium as quickly as possible. Okay, that corresponds to zeta equal to 1. Overdamped. Okay, overdamped for zeta greater than 1. Okay, and such a waveform, okay, as for negative zeta, typically zeta less than minus 1. Those who know all the cases of this control system, zeta less than minus 1. Okay, right. Between zeta 0 to minus 1, what comes? Okay, let me write down. When the zeta is between 0 to minus 1, such a type of waveform comes. Okay, which is oscillatory and increasing. Okay, understood. So correct answer here is A. You can just note this zeta negative. Any doubt here? Because when you convert to S domain, this will be 100 S square minus 20 S plus 1 Y, and that will go to the right side. Output upon input you will bring here. Okay, so transfer function of this system, if you wanted, okay, if you had written the transfer function, how this would have come? Transfer function y upon x in the S domain, right side, see, when you bring x on the left side, right side 1, and in Laplace transform, double derivative corresponds to S square, single derivative corresponds to S. So that is why this would become 100 S square minus 20 S plus 1, and that is where I told you negative zeta. That is where I told you negative zeta. Okay, that is where it has to be negative zeta. Okay, I am not doing further calculation, but hope when you calculate fully, the zeta should satisfy less than minus 1. That you can verify. Okay. Done. Next question. The steady state error of a unity feedback linear system for a unit step input is 0.1. The steady state error of the same system. Now see, unity feedback is anyways given. The steady state error of a unity feedback system for unit step input is 0.1. Okay, the steady state error of the same system for a pulse input RT given here, having the magnitude 10 and a duration of 1 second, a width of 1 second as shown in the figure. Okay. Now there are two ways to think about steady state error. Okay, unity feedback system. There are two ways to think about the steady state error. 2011 electrical 1 mark question. Okay, you can write down the steady state error as, okay, what is the meaning of steady state error? Okay, the steady state error means the error at steady state, which is limit t tending to 0, or sorry, limit t tending to infinity et. What is the standard definition of et? Error signal rt minus ct. And as per final value theorem, we write it as limit s tending to 0, s into es. Okay, now. So, on solving, we get, okay, these are the two common cases of steady state error. We get limit s tending to 0, s into rs. When we solve a unity feedback block diagram, we'll get es upon rs divided by 1 plus gs. Okay, this is one case. Okay, this is one case. Or, okay, or you can also say the steady state error, let's keep a very basic definition, limit s tending to 0, s into es. Now, what is es? If et is rt minus ct, okay, if et is rt minus ct, es becomes rs minus cs. The es becomes the rs minus cs, correct? It is going to become rs minus cs, right? It is going to become rs minus cs, okay? That is going to be es, okay? Rs minus cs. Now, what next? Okay, now rs minus cs, this is my transfer function. Okay, output is input into gain, input into transfer function. Okay, so when I substitute this, okay, I'll write down rs common, so s into rs, 1 minus transfer function, 1 minus ts. Okay, it is the same system. Okay, so even if you keep transfer function, that remains same, only input I have changed. Rather than step input, I have taken a pulse input. Okay, or if the same transfer function, same gs will be there. Okay, same gs will be there. Okay, so what is first of all given to me is, okay, the steady state error. Okay, if it is step input, okay, steady state error will become limit s tending to 0, s into rs. Okay, for step input, what is the Laplace transform? 1 by s. Okay, so s into rs upon 1 plus gs if I go by the first form. Okay, so you know, this means, okay, this actually is kp, you know, we can go to the kp concept also, but not required. Okay, not required here. Okay, this is how much? This is given to me as 0.1. Basically, this is going to become 1. This will cancel upon 1 plus kp. Okay, okay, where we define kp as limit. Okay, this is constant, this is also constant, so limit goes where? Limit is applied to limit s tending to 0 gs. Okay, no need to find kp, we can stop here. Okay, no need to find the kp, but I'm just telling that limit s tending to 0, limit s tending to 0 of gs is the kp, positional error coefficient. Okay, but what is the input given now? For the same system, if the input is the pulse input, rectangular input, how do you write down a rectangular signal? Let's you know, talk about this one. Okay, how do we write down this rectangular signal? That's what you know, let us try to understand. Okay, how are we going to represent this rectangular signal? Okay, so see this rectangular signal, please focus here. Okay, you know, of duration 1, where did it start? It starts at 1 and it ends at 0. Okay, so this can be written as, this rectangular input can be written as difference of 2 unit step starting at origin, unit step starting at 1. So ut minus 1. Difference of 2 unit steps of equal amplitude gives a rectangle. Okay, that will give a rectangle of 1 because I have taken unit step. I want width, I want magnitude 10, so I will multiply 10 here. 10 times this case. Okay, so yeah, what is the input I told here? Input, which is a rectangular pulse, is 10 times, because amplitude is 10, ut minus u of t minus 1. Ut minus u of t minus 1, correct? Okay. Now, what is going to be the Laplace transform? 10 into unit step Laplace 1 by s. Again unit step 1 by s, but time shifting e power minus s will come. Time shifting e power minus s. Okay, e power minus s. Okay, so overall input can be now written as 10 by s 1 minus e power minus s. 10 by s, 1 minus e power minus s. Okay, now what? Okay, now what is my steady state error? It becomes limit of s tending to 0, s into rs. Okay, what is rs? 10 by s, 1 minus e power minus s. S again cancel and whole divided by 1 plus gs. Okay, now s and s again cancel. What is left? 10. Okay, s tending to 0, so 1 minus e power minus 0 upon 1 plus gs. Now, what is this 1 plus gs or 1 plus kp? When I put limit s tending to 0 on gs, that becomes kp. But I told you that is why separately kp not required. Some kp will come here, but not required because this is 1 minus 1. Okay, this becomes 10 into 1 minus 1 whole divided by 1 plus kp. But this 1 minus 1 is going to make the answer 0. Okay, so answer to the question is 0, option number A, gate 11. Okay, electrical 1 mark question. Understood? Okay. Next question. The characteristic equation of a linear time invariant system is given by, okay, delta S is characteristic equation given to you. The system is BIBO stable. Gate 19 electrical 1 mark question, direct question. Okay, easier one on Rauther-Weights. Okay, because you need the range of K for stability. Anyways, okay, first range can be obtained from here only. Okay, necessary condition, before you apply Rauther-Weights also, necessary condition says that all coefficients must be of the same sign. Necessary condition says that all the coefficients must be of the same sign. Okay, that means all must be, okay, plus, 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 plus. Okay, so this tells you number 1, k has to be greater than 0. Okay, this is what we call it as necessary condition. Okay, necessary condition. Okay, all coefficients of same sign. Okay, right, not 0, same. Positive means positive. Okay, all coefficients of same sign and all present also. None of them must be missing. Okay, if I tell you something like s power 4 plus directly 3s square, then directly you can say such a system cannot be stable because it has a missing coefficient. Okay, that should also not happen. Now, for sufficient condition, this is necessary. Okay, you go to Routh array. Okay, you form Routh array. Okay, you form Routh array. So let's form the Routh array. Okay, let us form the Routh array here. Okay, what is my characteristic equation? I'll rewrite here s power 4 3s cube plus 3s square, 3s cube 3s square plus s plus k equal to 0. Okay, now I have s power 4 and s cube. Okay, so that is 1 and 3 and k, 1 3k and s square. Now s cube, sorry, this is the alternate terms taken. Then s cube, this is 3 and then this is 1 and 0. 3 and 1 and 0. This is going to be 3 and a 1 and a 0. Three and a 1 and a 0. Okay, now I'll form the s square row. Okay, so this is 3 3 9 minus 1 8. Okay, 8 divided by 3. Okay, 8 divided by 3. Then again we do the reverse cross multiplication here. So 3k minus 0 means 3k and always divide by first element of the above row. So it becomes 3k by 3, which is k. Last element of a row is always 0. Okay, and when I'm solving that reverse determinant also, first column is always fixed. When I'm finding this element, this is my next column. When I'm finding this element, this is my next column. First column will be fixed. Okay, right. Okay, so what is this? Just as a quick revision, I'll tell you. Okay, this is nothing but negative of the determinant. That is why we do the cross multiplication. It is negative of the determinant formed by first column and then the column next to this element, whole divided by first element of above row. Okay, similarly, how is this formed? Okay, this is formed as negative of the determinant. Okay, the first column will always remain fixed. Next column depends on this element. What I am finding, I will see the next to it. That is k and 0. Divide by first element of above row. Divide by first element of above row, that is fixed. Okay, this is the Routh-Harry pattern. Okay, now what is s raised to the power 1? Okay, s raised to the power 1 row. So, okay, 8 by 3 minus 3k. So, because of negative of determinant, normally you solve the determinant this way, 3k minus 8 by 3. But minus is there, so I directly solve reverse way. 8 by 3 minus 3k divide by 8 by 3. Okay, divide by 8 by 3. Then, now see here, this will be directly 0. Why? Because the entire next column is 0. And when the column of a determinant 0, answer is 0. Last element anyways will be 0. Now, last row, s power 0. Okay, suppose this is, x. Okay, x into k. This is anyway 0. So, x into k divided by x, divided by the first element. So, only k will be left. Okay, so this will be k. Again 0 because this column is 0 and last element always will be 0. Okay. Now, number of sign changes in the first column indicates number of roots in RHP, but you want the system to be stable. Okay, you want the system to be stable. That means there should not be any sign change in the first row of the Routh array. Okay, when you say, understand very clearly, when you say the system to be stable, okay, you want no RHP root. Okay, and at the same time, you also want no imaginary, no j omega access roots. Why? Because RHP root is known to make the system unstable and a pair of j omega access roots is known to make system marginally stable. Correct. Now, when you say no RHP roots in Routh array, that is equivalent to no sign change in the first column, because if there are sign changes, the number of sign changes will be the number of RHP roots. So, no sign change in first column of Routh array, and no j omega access roots means no ROZ, because j omega roots are only possible when you have row of zeros, a row which is entirely 0, which gives the auxiliary equation which may give us imaginary roots. Correct? This is what is the point to be noted here. Okay, so now see here, plus plus plus, you want no sign change, and no row of 0 also. That means what you want here, okay, according to us, this also, because all these are plus, this also must be positive, not even 0, because if it is 0, entire row will become 0. Sometimes 0 may be included in the option as a part of boundary case. Okay, marginally stable. Okay, but on the strict sense, it must be positive. This also must be positive. Okay, so what I want here, plus means 8 by 3 minus 3k must be greater than 0. And here k. Acha, k anyways I told must be greater than 0 for necessary condition also. Okay, so when I solve this one, I'll get what? 3k. 3 I divide here. So k will become less than 8 by 339. And this will give you k greater than 0. So what is my final range of k? K has to be greater than 0 but less than 8 by 9. K must be between the 0 to 8 by 9. K must be between 0 to 8 by 9. You can tick mark option number A, right? Correct, Sirisha. Option number A is what you can directly tick mark here. Okay, everybody? Option number A. Okay. Next question. Yeah. The open loop system represented by the transfer function, okay, is what? Now, they are directly asking, okay, this is some open loop system represented by this transfer function is what? Okay, we have to comment on the stability of this transfer function only, stability or minimum or non-minimum phase. Okay, non-minimum phase or minimum phase. They are not telling that a closed loop system represented by this open loop transfer function. No, so we have to talk about open loop system represented by this transfer function is what? Okay, now for stability, I directly need poles. There is no role of zeros in stability. So poles are -2, -3. Okay, so all poles LHP, stable, finish, direct. It's like a very basic 1 mark question. Okay, Gate 11 electrical 1 mark. Okay. If I write down zeros is S equal to 1 RHP. If pole or 0 anything is in RHP, the system cannot be minimum phase. It is non-minimum phase. Stable but non-minimum phase. So your tick mark answer is B. Okay. Because what you know is for stable, only you need poles. All poles in LHP. All poles in LHP. For minimum phase, what you need? Okay, all poles and zeros must be in the LHP. All poles and zeros must be in the LHP. Right? Correct. So option number B. It has to be option number B. Okay, Manasan, option number B will match up here. Okay. Stable but non-minimum phase type. Next question. Right. Okay. The root locus plot for a system is given below. What is the open loop transfer function? See, root locus is the locus of roots of characteristic equation, but anyway, we draw it using the help of open loop transfer function. Very easy question. Okay, it's a very basic, even very basic root locus analysis. Okay, which is showing you, that there is a pole at origin. Okay, that there is a 0 at -1. There is another pole at -2. Okay, and then there is pole at -3. And then there is the pole at -3. Okay, right. So because there is a 0 at -1, so there should be a s plus 1 term in the numerator. There should be a s plus 1 term in the numerator. Okay, so there is no need of this s minus 1 term. Now there is a pole at origin. Pole at origin means the s term should be denominator. This term is wrong here. Okay, this term is wrong here. Okay, this term is wrong here. What else? Okay, now, okay, there is a 0 at -1, there is a pole at origin, pole at -2, but s plus 3 or s plus 3 square. Okay, there are the two odd answers here, B or C. Okay, how do we identify? Okay, how do we identify -3 has a single pole or double pole? Okay, I think in this question there is a typo error, because as far as I remember the official question gate 11 EC, okay, there was no double arrow shown. That we have to figure out. Okay, but you know, it looks like double arrow. It was not actually in the question. There was some arrow at -3 shown. Okay, there was only the arrow at -3 shown, not like a double arrow. Okay, single arrows were shown at each of this location. Understood? Okay, now tell me whether there is a single pole at -3 or a repeated pole. The point here to be used, this is the main point where root locus will come. Otherwise, it is a pole zero diagram based question that you can wrap up here. Because what are the poles and zeros we plot in the root locus is the open loop pole and zero only. That comes into the picture. Okay, because we know that root locus, okay, it is the locus of roots of characteristic equation, but root locus always starts from open loop poles of GSHS, and it always terminates at the open loop zeros or infinity. Now, please see here very clearly what is shown in the question. Root locus exists here as well, root locus exists here. Root locus existing on both sides of this pole. This is only possible for a repeated pole. Why? Because, okay, there is something in root locus, you call it as, there is something in root locus which we call it as odd number criteria, which talks about, okay, which talks about the fact that the root locus will exist on the section of real axis The root locus will exist on the section of real axis. Where will it exist on real axis? Okay, where, okay, the total number of poles, where the total number of poles and zeros towards the right, of that section is an odd number. Total number of poles and zeros towards the right of that section is an odd number. Towards the right of that section is an odd number. Understood? Total number of poles and zeros towards the right of that section is an odd number. Done? Okay. Is an odd number. Now let's see. Okay. Let's see forward what is going to happen here. Okay. So see, when, if I take this root locus diagram, okay, as I told you, okay, this is a pole. Okay, but whether it is a single pole or repeated pole, that's what we are trying to figure out. Now see, root locus exists here also. The arrows were shown. Okay, those are the branch arrows. How many poles and zeros are seen to the right? Total, pole and zero, total you have to combine. So this is 3. Okay, which is odd. That is why root locus exists here. Okay, when I see from this section of real axis, 1, 2, 3, 4, it looks like 4. But 4 is an even number. 4 is an even number. And if it was actually even number, root locus should not have existed here. There should not be any branch or branch arrow shown here. Okay, so definitely it should not be 4. Okay, it will be 5, considering this as double pole. This has to be 5, considering this as double pole. And 5 will be odd, and only when it is odd, only when it is odd, then only the root locus will exist there. Okay, so that clearly says that S minus S at S equal to minus 3, there is a double pole, and that takes you towards this option number B. Understood the concept behind this one? Okay, so it's not only a simple pole zero. Yeah, first level is it's a pole zero diagram question. Okay, other than root locus, but the odd number criteria, where will root locus exist on the real axis, that also has to be figured out. Okay, that also has to be figured out. Done? Let's go ahead to the next question. Yeah. Figure shows the Nyquist plot of the open loop transfer function GSHS of a system. If GSHS has one right hand pole, okay, what does this statement mean? If GSHS has one right hand pole, okay, number of poles of GSHS, okay, in the right side is 1. Okay, this is what I define it as P plus. Okay, P plus. Okay, and then when we talk about the stability, I'll define all the things. What about the closed loop system? Okay, with reference to Nyquist plot. Okay, what is the stability analysis formula from Nyquist plot? N equal to P plus minus Z plus, or N equal to Z plus minus P plus, depends on what? If it is clockwise, okay, which they have not mentioned. Normally in the recent gate questions they would clearly mention, otherwise this question becomes ambiguous. If it is clockwise Nyquist contour, or if it is anti-clockwise, or if this one is anti-clockwise Nyquist contour, this is the formula we use. Okay, this is the formula we use. Okay, now, okay, P plus. Now, what is P plus? Let me generally define these parameters, whether this case or this case. The parameter meaning is same, is the number of poles, okay, of GSHS, okay, in RHP. Okay, in the RHP. That's why I simplify, I write it as plus. Plus means the positive side area, the right hand side area. Okay, what is Z plus? Z plus is the number of zeros, okay, of not GSHS, of 1 plus GSHS in RHP. Now, zeros of 1 plus GSHS means 1 plus GSHS becomes 0. And if 1 plus GSHS becomes 0, okay, that is characteristic equation. Okay, so we can also say that Z plus is nothing but roots of characteristic equation in RHP. Okay, and then what is N? n is given by the number of encirclements, of the critical point -1, 0, okay, by the Nyquist plot. Where n also has a sign convention that n is taken as positive for anti-clockwise encirclement, negative for clockwise encirclement. Okay. That is what is given. The GSHS has one right hand pole. Okay, the number of poles of GSHS in the right side, that is what is P plus. The question says P plus. Okay, now closed loop system is stable or what? Okay, what do you want for stability? Z plus is the roots of characteristic equation in RHP, and okay, Z plus must be 0 for what? For stability. Okay, because stability says that there should not be any root of characteristic equation in RHP, because even if there is one root of characteristic equation in RHP, the response is unbounded, system is unstable. Okay, so we want Z plus equal to 0. Okay, the closed loop system is stable. Okay, if Z plus equal to 0. Okay, now what is the number of encirclements of which point of this critical point -1, 0? Now, if you see here, okay, the Nyquist plot makes one full encirclement, one full rotation about this point, but it is in which direction? Okay, anti-clock. Okay, anti-clock. So this point I will mention here separately. This point is clearly encircled here once. Okay, in anti-clockwise sense. Once in the anti-clockwise sense. That means the number of encirclements would be taken as positive 1. If it was clockwise, I would have taken negative 1. Okay, I would have taken negative 1. Okay, but here it is anti-clockwise. Okay, everybody. Okay, so now when I go and apply the formula, n equal to p plus minus z plus, n is equal to 1, p plus equal to 1 minus z plus, okay, giving you 1 and 1 cancel, giving z plus equal to 0, which indicates stability. It is stable. Okay, it is stable always. Okay, because always means even if the gain, okay, suppose there is some gain at omega 0, even if the gain of the system is increased, okay, it would, this point will keep shifting, but still the number of encirclement remains to be 1. That is not going to be affected. Okay, but yes, what? Okay, so what if the formula, if I use as n equal to z minus p, okay, where n is 1, okay, p plus is still given 1 and z plus will become 2, okay, that will become unstable, okay, with 2, okay, closed loop right hand poles, because roots of characteristic equation means what? This also should be clear to everybody. Now, what is the roots of characteristic equation? Roots of characteristic equation are simply known as the poles of closed loop transfer function. Okay, so the system will be unstable with 2 right hand poles. Then it would take you towards answer C. Okay, if this was a question in recent days, definitely we can challenge this question. Okay, and IIT will challenge also. But recently, if you see the questions that they are producing, definitely they are being very clear in the language with respect to the contour. Okay, directly or indirectly. Otherwise, they will give some hint. Otherwise, they will give some hint about Nyquist contour, whether it is clockwise or anti-clockwise contour. Whether it is clockwise or anti-clockwise contour. Some hint would be given. Okay. But if not given, normally as per some standard Indian author books, I don't say generally, okay, clockwise Nyquist contour is the by default rule, the questions used to come in the earlier era also. Okay. Right. So we'll go with option number A right now for the question. Okay. Take Nyquist, contour if nothing mentioned. Okay, but recent questions will be more careful about this. Okay, if nothing mentioned. Done. Okay, find here. GATE 2003 EC 1 mark question. Okay. For the transfer function Gj omega 5 plus j omega, the corresponding Nyquist plot. Now see, this is very simple. GATE 11 EC 1 mark. Why? Because Nyquist plot is the plot of what? GSHS only. Now, they've converted directly into frequency domain and given it. Okay. Now, out of this, okay, there is something which is constant. The real part is constant. Okay. The real part is given to you as constant. Okay. The real part equal to constant. Now, what is the real part of S actually? It's like sigma equal to constant. Okay, that is, okay, sigma equal to constant. And sigma means, okay, sigma means x-axis. Real part of any complex number is plotted on x-axis. Okay, right. So, real part is given to you as constant. Okay, so what should be the corresponding answer then? Okay, real part if I take at sigma only, actually the real part of Gj omega should be Re, real part of j omega, Re of Gj omega. But okay, understood the intent of the question. And whenever the real part is constant, how will the Nyquist plot look like? Okay, how will the Nyquist plot look like? Okay, right, x equal to constant. Okay, whenever x equal to constant, okay, real part equal to constant means it's as simple as x equal to constant, because the real part we plotted on the x-axis, and x equal to constant, this equation x equal to constant represents a line, okay, parallel to y-axis, parallel to j omega axis. Okay, so option number A. Okay, option number A. Okay, but yeah, I'll tell you, this question again has a fundamental problem. Okay, this question has a fundamental problem. Answer is A, that you can tick mark during exam time. But this, they are asking Nyquist plot. Nyquist plot is the plot of GSHS, which is plotted in GSHS plane. It is not plotted in S plane. Okay, if it was S plane, I could have told real part sigma, imaginary part j omega. Okay, this should be actually, okay, this should be GSHS plane. This should be GSHS plane, and this is simply named as real axis, real part of GSHS, and this is simply named as imaginary axis of that particular plane. Okay, sigma and j omega comes in the S plane actually. So there is a conceptual error here, but yeah, the intent is still clear. We can still solve the question. Okay, that real part is constant. Okay, Gj omega for positive frequency, as omega keeps on increasing, the imaginary part keeps on increasing, but real part, okay, is fixed at 5. Okay, the real part is fixed at 5. Okay, so this shouldn't be sigma, this shouldn't be named as j omega. That is what I am telling. What should be rather written in the question? Real axis and imaginary axis. Okay, real part will always be 5, imaginary part for positive frequency if omega, that's why clearly mentioned. Okay, Nyquist plot for positive frequency means polar plot. Okay, so as omega increasing, imaginary part will keep on increasing. Okay, and that means it will keep going towards the positive y direction. Understood? So, some fundamental flaws, if there have been in the question, that I am telling you. Okay, this was GATE 11 EC 1 mark. The previous one was GATE 2003 EC 1 mark. That also had a very minute flow, but then for the previous question, we went with the flow. The by default, nothing mentioned. We took the clockwise contour, Nyquist contour. That is still okay. This also is solvable. We know what type of diagram is come. Okay, while writing the real and imaginary part, they have done some basic mistake here. But okay, the question is still solvable. You understand, you can tick mark. Okay, GATE 2011 EE 1 mark question. Okay, the frequency response of a linear system is provided in the tabular form. What is the gain margin and phase margin of the system? Okay, gain margin is calculated where, phase margin is calculated where. Okay, gain margin is calculated at phase crossover frequency, okay, omega p, and phase margin is calculated at grain crossover frequency, that is omega g. Okay, right, it's a very fundamental definition question only, but if I write down, see, what is actually gain margin? Okay, absolute gain margin, or in decibel only I'll write, in decibel, or okay, first I'll write down the gain margin. Gain margin is actually given by 1 upon magnitude at omega p, 1 upon modulus dj omega p at j omega p. Okay, or in decibel, okay, that is the standard unit for gain margin. It is expressed as 20 log of this value. 20 log 1 upon mod of Gj omega p h j omega p. Okay, h j omega p. Now, if that is the case, okay, if that is the case, first of all, what is omega p? Omega p, we call it as phase crossover frequency. How do we calculate phase crossover frequency? Okay, how do we calculate phase crossover frequency? At omega equal to omega p, the phase of the system, the angle Gj omega at j omega, okay, has to be equated to 180 plus or minus 180, anything is okay, because it is the point at which the Nyquist plot intersects the negative real axis. Okay, phase crossover frequency. Okay, Nyquist plot, or I'll write down in terms of polar plot. Polar plot intersects, okay, negative real axis, and that is why the phase at that point is 180, plus or minus anything, okay. Okay, now phase margin is calculated by 180 degree plus angle of Gj omega g Hj omega g. Okay, where omega g is what is the gain crossover frequency. Okay, and what happens at omega g? How do you calculate omega g? I mean, okay, you have to take the magnitude function, okay, mod Gj omega Hj omega, and put it equal to 1. At omega g, the magnitude will be 1, because primarily this is the frequency at which the polar plot intersects unit circle. At which the polar plot intersects the unit circle. At which the polar plot intersects the unit circle. Now, okay, this is a definitional based question only. See why? Because, okay, suppose gain margin. Okay, suppose gain margin. So see, gain margin is calculated at omega p. Okay, what is omega p? Okay, omega p is the frequency at which angle becomes plus or minus 180 degrees. So here frequency not given, directly magnitude and phase given. Okay, but this is the frequency. Okay, there is some frequency not given, but where the phase becomes minus 180, magnitude is given. Okay, so this is the omega p point. This is not omega p value, but at this frequency, okay, some frequency will be there where phase is minus 180. So now I need, okay, this magnitude. This will give me gain margin. Okay, this is corresponding to, this is what is corresponding to omega p. So what is the gain margin? Options are in decibel. Okay, so take 20 log. What I told you, the gain margin is 20 log 1 upon magnitude at omega p. So at the same frequency, what is the magnitude? 0.5. Okay, so this becomes 20 log 2, which is going to be 6 decibel. Okay, now only by one calculation I will tell you tick mark option number A. Why? Because if gain margin is positive, phase margin will also be positive. Always remember, okay, for a stable system, if it is a stable system, okay, gain margin and phase margin are both positive. Gain margin means decibel gain margin, and phase margin standard unit is degrees. Okay, if it is unstable, not only one of them, both will be negative. For unstable system, both the GM and PM will be negative. Okay, and if it is marginally stable system, oscillatory system, both the gain margin and phase margin will be 0. Gain margin 0 decibel, phase margin 0 degree. Okay, that is what also you should know. Okay, so if gain margin is positive, phase margin will also be positive, and that is only in one option. Okay, right, B and C type of option not possible, one positive, one negative. Right, acha, now still let us find out how it is phase margin 30. So see here, phase margin, as I told you, is calculated at omega g. Okay, and what is the omega g? At which magnitude? Here only hj omega not given, means unity feedback. Okay, this is the frequency where magnitude, okay, mod gj omega should be 1. Okay, so where is the magnitude 1? Here. Okay, this corresponds to, I will say that this is the value corresponding to omega g. Okay, right. Now I need the phase at this point, and then I will write down the phase margin. See, what will be my phase margin? I told you the formula just now. 180 degree plus, phase margin is 180 degree plus the phase of the system at omega g, angle omega g. Okay, so this corresponds to omega g. What is the angle here? Minus 150 degree. So 180 plus minus 150 degree. That is how it becomes 30 degree, which is anyways there in option number A. Which is anyways there in the option number A. Understood all? Okay, option number A. 6 dB and 30 degree. Okay, the 6 dB and 30 degree. Right, let's go ahead to the next one. The gain margin for the system with the open loop transfer function GSHS 2 1 plus S. Okay, 2 1 plus S upon S square. Now see here, GATE 2003 EC 1 mark question this is. Okay, see, I need the gain margin. Okay, and the gain margin is primarily calculated at omega p. Okay, let's convert this function into frequency domain. What do I have here? I have gj omega hj omega, that will become twice of 1 plus j omega, 1 plus s equal to j omega upon j omega whole square. Okay, or I can say j square is minus 1. Okay, that way also I can say. So let me first write down magnitude and phase both. What is mod gj omega hj omega? Okay, 2 complex number magnitude root over x square plus y square. J omega magnitude is omega, but square it is. Okay, then what is the angle gj omega hj omega? Okay, the angle will be tan inverse. Okay, now see, j omega 2 times. Okay, denominator, any phase I write negative, but j omega imaginary phase is 90. Okay, j omega 2 times, so that will be minus 180 degree. Okay, it's like minus 2 times 90 degree, and then plus of tan inverse omega, tan inverse y by x. Okay, so this phase part, okay, let me call this as magnitude, let me call this as phase phi. Okay, the phase part is actually minus 180, okay, plus tan inverse omega. Now this is a special and important case, okay, because for gain margin we need omega. Okay, and how do you calculate omega? You equate the phase to minus 180. Okay, and as soon as you equate the phase to minus 180, our phase expression, which is minus 180 plus tan inverse omega at omega p. Okay, this is minus 180. So 180, 180 cancel. Okay, tan inverse omega 0. So omega also becomes 0. Okay. Okay. Right. Now, there is a special case that you should know, that whenever omega p tends to 0, okay, don't trust the gain margin formula. Why? Because I'll tell you. Why? Because I'll tell you. Because here, okay, if omega p is 0, see what is the magnitude of the function. Now, because omega 0, okay, magnitude will become 2 into under root 1, but divided by 0, which tends to infinity. Okay, then, okay, magnitude infinity, this also correct. Then if you say that gain margin is 1 upon this magnitude, absolute unit, decibel also we can convert. Okay, you say that the system gain margin is 0, 1 upon infinity. Okay, this particular point, okay, specifically this particular point I want to highlight. Here you go wrong. Okay, here you go wrong. This is something that you have to avoid. Why? Because Okay, when you say, okay, omega p is 0, but what is the magnitude? Okay, if you take here magnitude tending to infinity, okay, so does it actually cut the negative x-axis? Because I told you the real definition, okay, of phase crossover frequency is the point at which polar plot intersects the negative real axis. Okay, to intersect negative real axis, it will intersect at some point, na? But what is that point? It has infinite magnitude. Can anybody reach infinity? Can anybody reach infinity? Magnitude tending to infinite means the polar plot actually would never cut. It do not intersect the negative real axis. It do not intersect the negative real axis. Okay. Now, okay, I'm telling you, if omega p 0, don't trust the gain margin formula. So you have two choices. Okay, if you can't use the gain margin formula, you have two choices. Okay, what are the two choices? What are the two choices? The two choices are, if I write down the characteristic equation of the system. Characteristic equation is what? 1 plus GSHS equal to 0. Okay, 1 plus GSHS equal to 0. Okay. Right. Or, you know, the gain currently is 2. The gain currently is 2. Gain margin is all about how much gain you can increase for the system. Okay. First, I will draw the Nyquist plot and then we will, you know, come to this characteristic equation also. Nyquist plot. See, what is the GSHS given to me? It is twice of 1 plus S upon S square. Okay. See, for omega tending to 0, okay, that is starting phase. There are some shortcuts. You can follow my full videos on polar plot and Nyquist plot. I'll just use, okay, that starting phase when omega tending to 0. Okay, the starting phase is given by minus 90 degree into n, where n is the number of poles at origin. Okay, n is the number of poles at origin. This is minus 180 degree. See, that you can tally from here also. Anyways, I have written the angle expression for you. Tan inverse 0 is 0. How much phase? Minus 180 degree. Okay, how much phase? Minus 180 degree. Then omega tending to infinity. For many times, the starting and ending frequency is enough. We call it as theta ending or theta diving. Okay, because at omega infinity, magnitude will be 0 and we dive into origin. Okay, at omega tending to infinity, magnitude will be tending to 0, na? Okay. Okay, because omega infinity, 1 upon infinity 0. Magnitude 0 and magnitude 0 means origin. I call it as D, dive into origin. Okay, and that is given by minus 90 degree into P minus Z. Minus 90 degree into P minus Z. P is the total number of poles, Z is the total number of zeros. Okay, total number of poles, 2. Total including origin, and if there were some other poles also. Z, total number of 0. So only 1 0. So how much this becomes? Minus 90 degree into 1, which is minus 90 degree. Okay. So minus 90 degree, when I dive into origin, minus 90 degree axis has to come, that is negative y axis. Okay, and this is towards negative x axis. How the Nyquist plot of this function will look like, just an approximate basis. For analysis, this is a good question actually. Okay, so starting, okay, I already explained to you at the omega tending to 0, how much will be the magnitude? Magnitude is tending out to be infinity. That's what I've already written there. Magnitude is infinity at omega 0. Excuse me. Okay. At omega infinity, that is dive into origin. But when you dive into origin, origin is connected to all four, positive and negative x-axis, positive and negative y-axis, but phase tells that phase is minus 90, so I will come along negative y-axis. Okay, so I will dive into the origin so that it looks like I am almost coming from negative y-axis. I'm just touching here. Okay, and starting is negative x-axis, actually parallel to negative x-axis, because magnitude is infinity, so you can't actually touch the negative x-axis. Okay, so the polar plot of this one will be approximately of this kind. Okay, approximately of this kind. Okay, this is omega 0 and this is omega infinity. Okay, now this is only polar plot. Let me call it as 0 plus and infinity plus, positive frequency. Okay, then to complete the Nyquist plot, we take the mirror image. We'll take the mirror image of this. This is 0 plus, mirror image will be 0 minus and infinity minus. Then we join from 0 minus, okay, to 0 plus in clockwise direction through an angle of n pi. Okay. N pi here will be 2 pi because n is 2, number of poles at origin. Okay. So, if you see this point minus 1 comma 0, it is nowhere encircled actually. Okay. It is not going to be encircled here. Okay. I told you Nyquist plot do not intersect the negative real axis, and that is why you are able to see that minus 1 comma 0 not encircled. Okay. It is not encircled. So n is equal to 0. And now already if you look into this particular transfer function, what is the p plus? P plus is 0. P plus is 0 because there are no poles in the RHP. There are only 2 poles at origin, but P plus is number of poles of GSHS in RHP. So even if I apply the formula n equal to P plus minus Z plus or n equal to Z plus minus P plus, anything if I apply, n is 0. Okay, whatever contour is given, P plus is also 0 for the question. So if you feed into any of the data, Z plus is 0, system is going to be always stable. Because even if you increase the gain, okay, it will, it is not going to intersect anyhow the negative real axis. Infinity into k will remain infinity. Okay. The possibility comes when suppose this was the polar plot. It is cutting the x-axis here at some magnitude. Suppose it is minus 0.8. There is the risk. If you now increase the gain, right now there is no encirclement if I take the mirror image also. But if I increase the gain now, okay, it may come here, it may come here. Okay, now minus 1 comma 0 encirclement. If n value comes, z plus will be equal to that n here because p plus is 0. System can become unstable on increasing the gain. So gain margin talks about that particular gain only. How much is the margin in your hand, okay, by which you can increase the gain of the system, and here it is, okay, infinite gain margin. Gain margin here is infinite. Okay, gain margin here is infinite. Okay, same thing I was trying to explain you with the characteristic equation also. 1 plus GSHS. Okay, so 1 plus 2, 1 plus S upon S square given. Okay, I am making the gain now 2k. I am trying to increase the gain. Okay, still how my characteristic equation will look like? S square 2ks plus 2k equal to 0. Okay, this is clearly indicating second order. Zeta is positive. Okay, for any k greater than 0. Gain k we increase as positive only. Okay, so by how much factor you can increase the gain k? Okay, whether you take k 10, if you want you take k 100, if you want you can take k any large value. Okay, right, this is what is suggesting that the system has infinite gain margin. By how much margin you can increase the gain of the system before it becomes unstable? It is not going to become unstable. Okay, because its zeta is going to be positive for any k. Okay, so yeah, important line that I have noted for you is when omega p is 0, don't trust the gain margin formula. That is the exceptional case. You should please note down. Okay, because blindly if you applied the gain margin formula, you would have told 1 upon infinity 0 gain margin. System does not have any gain margin. Rather, this system has reverse infinite gain margin. Okay, so the answer that I will tick mark here is option number A, that is infinity. That is going to be infinity. Done? Next. Okay. The open loop transfer function of a unity feedback system is given pi e power minus 0.25 s upon s. In the GS plane, the Nyquist plot passes through negative real axis at which point? Okay. So the question is talking about Nyquist plot crossing the negative real axis. Okay, this happens at omega p, and we need to find out the point here. Okay, but where negative x-axis means omega p, we first have to find omega p. Okay, so what is the GS given here? Or I'll convert to the frequency domain directly. Gj omega pi e power minus 0.25 s, put s equal to j omega divided by s, that is s equal to j omega. What is modulus Gj omega? pi, e power j theta magnitude is 1, j omega magnitude omega. Okay, what is angle g j omega here? Angle, phase. Okay, pi to constant. For e power j theta, theta is the phase. But remember, e power j theta, when you are writing theta as the phase, this is normally in radians, standard units. So denominator, okay, we subtract the phase, pure imaginary 90 degree. So if one is radian, let's not write down the other one in degree. 90 degree is pi by 2. Okay, is pi by 2. The first thing I will do is I will calculate the omega p. Okay, I'll calculate omega p. Okay, at omega equal to omega p, the angle gj omega becomes minus 180 or minus pi, because everything is in minus, I'm taking minus pi. Okay, and wherever the phase is minus 1 minus pi, that is where the negative real axis comes. Okay, so minus 0.25 omega p minus of pi by 2, I have to equate to minus pi. That means 0.25 omega p will become minus minus cancel, pi minus pi by 2 will be pi by 2. So what will be omega p? This is like 1 by 4, when you send on the other side 4 pi by 2, that is 2 pi. This is omega p. Okay, but what is the magnitude of the system at omega p? What is the magnitude at omega p? Okay, it will become pi upon 2 pi, because magnitude is pi by omega, that is 1 by 2. Okay, so what is going to be the point? Because it is negative real axis, magnitude is 1 by 2. Okay, but because it is going to be plotted on negative real axis, so what is the actual x coordinate? Okay, actual x coordinate is minus half and comma 0, because negative real axis point. So minus half comma 0, minus 0.5 comma j0 in the complex point format. Okay, minus 0.5 comma j0. Option number C is what you can tick mark here, right? Option number C is what you can tick mark here. Okay, next one. Gate 19 EC 1 mark question, simple one on Bode plot. For the LTI system, the Bode plot of its gain is as illustrated in the figure. The number of system poles NP and the number of system 0 NZ in the frequency range 1 Hz to 10 power 7 Hz is how much? Now see here, Bode plot, basic analysis that is required to solve this question is, very basic analysis is, see here, this is the initial part. Anyways, they are asking the slope from 1 Hz. Okay, 1 will be before this 10 only. But yeah, this is the initial slope. Okay, what is the role of initial slope? Okay, initial slope 0 represents there are no poles at origin. They are asking the number of system poles. Okay, initial slope which is given by minus 20n, which is 0 here, that means n equal to 0. N equal to 0 pole at origin. N equal to 0 basically means, okay, n equal to 0 basically means there is no pole at origin. That is one thing sorted out. Okay, now wherever there is slope changes, that is either a pole or 0. Okay, a simple pole, whenever you see a simple pole means pole of first order. Okay, if you see a simple pole term, okay, you will see a slope change of how much? You will see a slope change of minus 20 decibel per decade corresponding to a pole. Okay, for a simple 0, there is a slope change of plus 20 decibel per decade. This is the very fundamentals of the Bode plot. Very fundamental of the Bode plot. Okay. So if I keep observing only the slope change points and see here there is a slope change of from 0 to minus 20. There is a slope change of minus 20. So this is one pole. Okay, minus 20 to minus 60. How much is the slope change? Minus 40. Slope decreasing means pole, but decreasing by minus 40 at 2 points. So this is 2 poles here at the same location. Okay, that is at the frequency 100. Then minus 60 to minus 40, how will you get? You will do plus 20. Okay, and when you are increasing the slope by plus 20, that has to be a 0 point. Okay, so this is 1, 0. Then minus 40. Now please see here. This slope was minus 40 and this slope is how much? This slope is parallel to x-axis, means 0 decibel per decade, and minus 40 you will have to do plus 40 to come to 0. Plus 40, and plus 40 will be done when there are 2 zeros here. Okay, now slope is again minus 40, so 2 poles here. From minus 40 to minus 60, again minus 20. Okay, so again one more pole here. Okay, and there is no more slope change shown. Okay, anyways, the question is up to 10 power 7. Okay. Now let's count how many poles. Okay, 1, 2, 3, 4, 5, 6. 6 poles are there and zeros. Okay, 3. Okay, 6 poles and 3 zeros. My answer is option number B. My answer here is option number B. 6 poles and 3 zeros. Understood? Fundamental question. Okay, just slope change concept corresponding to a pole or zero. Option number B. Okay, a PD controller is used to compensate a system. Compared to uncompensated system, the compensated system has what? Okay, see, PD controller, okay, which always, okay, adds, okay, a open loop 0. It always adds a open loop 0. It always adds an open loop 0, okay, which increases stability, which improves stability, because overall poles of the system, root locus is bended towards the left half plane. It improves stability. That is number 1 point. And also, okay, also it improves the transients. It improves the transient part. Okay, it degrades normally the steady state part. Why? Because normally, because of this, steady state part can increase. Okay, the steady state error can increase. Okay, but yeah, let's talk about the positives here. Okay, it will improve the transient. Okay, okay, because if we use it as a PD controller, not only D. Anyways, D controllers are never practically used. Okay, so that proportional part can handle the accuracy, the steady state part. It improves the transient. Why? Because it will increase the zeta. No need to remember the formula. There is some formula, but okay, some basic conclusions are important here. It increases zeta. Because of that, overshoot decreases. Okay, the fluctuations, the overshoot decreases. The rise time and settling time also decreases. Okay, that means the transient part gets over shortly and the system reaches steady state quickly. And whenever rise time decreases, bandwidth increases. And bandwidth increases, this automatically brings upon the case that there will be higher noise amplification, because noise is generally what is a high frequency component. Okay, so bandwidth increasing means it allows more of high frequency terms. It will allow more of noise. Noise becomes amplified. Okay, that is one point to be noted here. Correct answer is option number C. Okay, a lead compensator used for a closed loop controller has the following transfer function for such a lead compensator. Now see, for any transfer function to behave as lead compensator, it has to be zero dominant and lag means pole dominant. This is one regular type of question from lead or lag compensator. This is GATE 2003 electrical 1 mark. And zero dominant means zero must be closer to origin, okay, in left half plane only, okay, as compared to pole. As compared to the pole. As compared to the pole, right? Zero must be closer to the origin as compared to the pole. Correct? Now see, what is the pole and what is the zero for this function? Okay, 1 plus s by equal to 0, you'll get s equal to minus a. Okay, and the pole will be s equal to minus b. Okay, who is closer to origin? Whose magnitude is smaller? That means when you take the magnitude, this will be a and this will be b. Okay, so what you want? A to be less than b. If you want it to be a lead compensator, okay, A has to be less than B. Okay, if reverse happens, it will become pole dominant. It will become pole dominant and that will be a lag compensator. This is one regular question, just identifying lead or lag compensator based on the pole zero location. Okay. No role of the K here. Option number C and D are just randomly created here. Okay. Correct answer is A. Steady state error. Okay. Sorry, state space analysis. I'm so sorry. Okay, there is one question of state space analysis, 1 mark. Then there will be 2 mark question. Of course, this is only 1 mark question and this is the last question for the day. There is only one question from state space analysis, which is 1 mark category. Okay, GATE 2003 electrical 1 mark question, and that too simple only. A second order system starts with initial condition 2, 3. Okay, without, see here important word, without any external input. Okay, that means you have to consider zero input case. Okay, the state transition matrix is directly given. Okay, state transition matrix, which we normally call it as phi t or e power at. Okay, which is directly given to you. Otherwise, normally we solve it using the formula inverse Laplace transform of Si minus a whole inverse. Okay, the state of the system at the end of 1 second. Okay, so what describes the state of the system? State vector. Okay, state vector. Okay, and the state vector in zero input condition ZIR, okay, is simply given by phi t into x naught. Is simply given by phi t into x naught. This question is only on this calculation. Okay, so this is going to become, okay, phi t is given e power minus 2t, 0, 0, e power minus 2t, diagonal case, and x0 initial state, okay, is starts with the initial condition that is given as 2, 3. Okay, if I just multiply, what I am going to get, first row, okay, e power minus 2t into 2, this is 0, so 2 e power minus 2t. Then second row 0, and then 3 e power minus t. The state of the system at t equal to 1, the state of the system at t equal to 1 will become 2 e power minus 2, 3 e power minus 1. That's it. We just have to, finally do a bit of calculation here. Okay, the first term is approximately 0.27, and then you have 3 e power minus 1 is 1, approximately 1.1. Okay, so 0.27 and 1.1, option number A will match up here. Option number A. Okay. Let me specify very clearly with respect to EC and EE, all 1 mark question of these 3 years, 2019, 2011 and 2003. Okay, it's not selective, it's all questions including all chapters, whatever were asked in these 3 years have been correct, have been completed. Okay, and here, now we will have the next session where we will discuss 2 mark questions separately. Okay, now since we have revised today a few concepts, okay, that also, so see, you might have noticed that while solving questions, I am revising the required way to solve the question. So this session is not only question answer, but it is also helping you, okay, to revise and learn some concepts, the technique to solve the question. So we'll cover up the 2 mark questions in the next session. Okay, stay subscribed, and because we are in the flow of concept, I wouldn't keep much gap here. Okay, we are going to have the next session mostly on Wednesday. Okay, we're going to have the next session on Wednesday. That stands out to be what? 29th of July. Okay, mostly Wednesday we'll have that. Okay, right. So stay subscribed in case you want to attend all the sessions, and other subjects will also be going to be added up. Okay, so all 2 mark questions will be covered up here. Okay, again let me remind you, I told you in the beginning as well, the new offline batch at our Hyderabad center for electrical engineering starts July 29th. Okay, July 29th. So even several students, like even recent example, just last year also several students started preparation from July, but they were dedicated and honest enough, okay, with consistency, and they cracked ranks below 100. Okay, so at this point also, if you be serious and consistent, okay, you can be getting a very good rank in GATE examination. Okay, and the new offline batch, okay, for EC, okay, starts August 4. Okay, starts August 4. Okay, so this is what are the big updates for you, and we have been speaking about the benefits of offline, how a real classroom atmosphere in front of the faculty, okay, is grooming the ranks of the students. They make it more disciplined. They are in a competitive atmosphere that automatically boosts their preparation level. Okay, so you can enroll, and this is at our Hyderabad center. You can enroll, or for any queries you can contact 95156 94053 immediately. Okay, our team will guide you. Okay, and in case you cannot be at Hyderabad right now for any reason, okay, you think that it's not possible to make it to Hyderabad, okay, you can still get the guidance under the same faculty team, okay, by joining our new live batch that's going to start July 29th. Okay, for GATE 27 for both EC and electrical. Okay, the new batch starts July 29th. Okay, and okay, if you register till July 29th as well, okay, you can use the code OMGATE15 and get flat 15% early bird discount. Okay, flat 15 early bird discount. Okay, so that's also an option available. It's live interactive classes. Okay, and for the AEAEE students, the new offline batch, okay, for Telangana AEAEE or for AP AEE, okay, the new offline batch starts July 29th. Okay, right, these are some updates. Acha, one more thing is, whatever questions and concepts, formulas, whatever we have revised today, okay, I'm going to share you this entire PDF and I'll share it in my Telegram group. Okay, I'll share it tonight or maximum by tomorrow. Okay, but okay, my PDF in the Telegram will be password protected. Okay, and I have a simple logic. Those who have been watching my sessions, they know it. Okay, because you have been dedicated enough to watch this session. It has been already more than 1.5 hours, and probably when we take the 2 mark session, it is going to be taking little bit more time. Okay, because I'm telling you today also I covered all 1 mark question, not selective, ECEE, all 1 mark question of these 3 respective years which we have talked, IIT Madras years. Similarly, all 2 mark questions will cover. Okay, so those who are being dedicated, they are sincerely following the notes, and the PDFs are specifically and exclusively for those students. And if you are watching, you get the password. Okay, automatically. Okay, so what is the password? I'm keeping it as IITMCS1. Okay, everything in small. IIT Madras Control System 1. Everything, abbreviation I'm using. IITMCS1. Okay, 1 for 1 mark session. Okay, this is the password. Okay, you can note down, and I'll share the PDF which will have a password protection by tonight or by tomorrow. Okay, I'll share in my Telegram group. Okay, if you're not connected in my Telegram group, you can be connected here in my Telegram group. Okay, with this name mentioned. Okay, with this name mentioned. All right. Just for your convenience, I've also shared the link. You can directly join using the link. Okay, I've shared the link in the chat box right now. You can join the Telegram using that particular link. Okay, see you next in the 2 mark session. Okay, on Wednesday. Okay, control systems, and then we'll move forward towards the next subject. Okay, thank you so much. All the very best. Keep preparing hard.